In this video, we're going to talk about experimental probability. So we've done this exercise before where we've simulated rolling a die a certain amount of times. But now we're going to look at this through the lens of probability. So again, we can have our roll number and the value on die. And so our roll number, I'm going to start counting. There's one way to do it. We can start counting, and Excel knows that we're counting and will autofill this. But if we get to large numbers here, this is going to take a long time to drag down. So instead, what I'm going to do is I'm going to take the previous cell and add 1 to it. And I can copy this and I can paste it as far down as I want. And so the easiest way to do this, if I know I want to do something like 100 rolls, I can go down to A101 and put a stop there. You don't have to write stop, but you just need something in the cell. And then as I go down, if I Control-Shift down or Command-Shift down if you're on a Mac, it'll bring me down to that stop, and then I can paste. And, whoops. It will fill the roll number all the way down to 100. And once I know that I have 100 rolls, actually I think we're just going to start with 10 rolls, but I'm going to now simulate the actual roll of the die. So we're going to use the ran-between function. This gives me, excuse me, gives me a random number between 1 and 6. And for 10 rolls, this is what we end up with. Now the possible values that I can get are set. I can get a 1, I can get a 2, a 3, 4, 5, or 6. The number of times I see that, if this is a fair die, meaning it'll land on each side equally, we should see an even distribution. So I can count if the values in this column, which is the value on the die, are equal to this number. So there are two numbers that were a 1, and every time I copy or move anything or change anything in the spreadsheet, these random numbers regenerate. But you can see, if I have 10 rolls and I have 6 different numbers, I should see about 2 in each one and maybe 1 in the other, but I rolled 10 times and I never got a 5. And so doing probabilities, especially experimental probability, on a small scale doesn't give us any information. So there's something called the law of large numbers. Now I'm going to keep this data for roll 10 rolls. I'm just going to copy and paste this data. I'm going to copy, and I'm going to paste as a value so that they don't change. Okay? So in this case, these were my values. Actually, I'm going to do a different one because I just want it to be the one that we had before. So here we go. This is similar. I'm going to copy, and I'm going to paste the values. And what I'm actually interested in is the relative frequency. Now, relative frequency, we've talked about this before. That's just the number of times that the value came up divided by the total number of values that there are. So in this case, there's 10 rolls. If I sum up the frequency, I should get 10. So the relative frequency is going to be the previous number divided by the total number of rolls. I'm going to lock the reference to that hitting F4 on the keyboard. And then I can copy this down. Notice what happens when I sum up all of the relative frequencies. I'm going to get 1 every time. I'm going to get 1. Okay? Now, we should expect that all of the sides of the die are equally likely to come up. And so all of these numbers should be the same number, but these are not all the same. We have a 0.1, we have a 0.2, we have a 0.3, we have a 0, and we have a 0.1. But we only did 10 rolls. So what I'm going to do now is I'm going to expand this to be 100 rolls. Okay? So now we've done 100 rolls. And this is the frequency that, these are the values that we got. So if I copy this, and over here I'm going to do 100 rolls, I'm interested to paste the values. Oh, the values are gone, so now it's having me, oops. Having me recopy them. So I'm going to recopy, and then I'm going to paste special, but I'm going to paste just the form values. So those are the values. And again, I want the relative frequency. If I copy this formula down, actually if I copy both of these cells down, it should work. The problem being that it's no longer referencing we want this absolute reference to be that value. All right, so here are the relative frequencies after 100 rolls. So you can see these are a little bit closer together. There's no 0 here. It'd be very unlikely for me to roll a die 100 times and never roll a 5 or any of these numbers. But some are lower, some are higher. Now, what happens if I go to 1,000 rolls? So this is easy enough to do in Excel, because all I have to do is find cell A1001 and put a stop in it. And then I can take this cell, copy, Control Shift down, paste, and now I've counted to 1,000, and I can copy this down to 1,000, and now I have 1,000 rolls here. So you can see these numbers, even though there's variation in them, they are pretty close to one another. So I'd be very interested to know what the relative frequency is for these values, paste values. I'd like to know what the relative frequency is for 1,000 rolls. And this is just one instance. It's not necessarily true. So we're going to take, first we're going to find the sum. And again, we know it's 1,000, or at least it should be. So there were 1,000 rolls. We're going to take this, divide by 1,000, and all right, look at the variation here, much closer together. We did have more 3s than everything else, but our relative frequency for most part is right around 0.16. So as the number of rolls gets larger, what we end up with is a better picture of what the experimental probability should get closer and closer to the theoretical probability. And so we're going to do this one more time. I'm going to do it with 10,000 rolls. Okay? Oh, let's just go 100,000. Let's go big or go home. So again, I'm going to go to A 100,001. Did I do that right? Yeah. That did not bring me to the right cell. Oh, because I was still inside this one. All right. So we're going to go to 100,000. I'm going to go to A 100,001. And I'm going to put a stop there. And then it's much faster just to come up to the top here. A1 brings me back up to the top. So what I can do here is I can start here, I can copy, I can paste, and that should bring me down to 1,000. So now I can, 100,000. And you can see, if I were to scroll, this would take me a very long time. But I have 100,000 rolls of a die, and here are the totals. Okay? Now again, there's variation here, but the numbers are much closer together. They're all 16,000, so that's good. I'm going to copy. Over here, I'm going to paste my values, and then I'm going to find my relative frequency. And again, this is relative to the sum of the frequencies. So I'm going to take the frequency and divide it by the total number of rolls. In this case, the number of times I did my experiment. And all of these are in the 0.16. And 0.1666, I think if we kept doing this and we did 1,000,000 and 1,000,000,000, these would get closer and closer to 0.166 repeating, or 0.167. So that's, I mean, right here, this is the law of large numbers. You're seeing it happen right in front of you. 10 rolls, lots of variation. We can't expect anything to happen within the first 10 or even 100 rolls. But as soon as we get to 1,000 and 100,000, I skipped over 10,000. 10,000, you can imagine there'd be less variation than there was here. Maybe we'd still have the same 2 digits if we rounded being close to each other. But when we do 100,000, we are really close. Okay? What is 1/6? Which is the theoretical probability? That is 0.1666667. Okay? So what I was saying here is all of these, if we did enough trials, a large enough sample, then what would happen over time is this would finally approach 0.167. So that's the idea behind the law of large numbers. And the idea is if we only did 100 rolls, we can't expect the theoretical probability, the experimental probability to match up with the theoretical. But if we do 100,000 rolls or 1,000,000 rolls, we're going to see the experimental probability and the theoretical probability get closer and closer together. All right, I'll see you in the next video.